Looks like Daniel is with us.
Hello.
Hello, and Nicholas is with us. Good. Excellent. Who else we got here? Let's see. Oh, we've got a good crowd. We have Anna, Alex. I'm confused. This says Anna Wallace, and I have.
That's sorry. That's my wife's name. This is Nathan. I can try to switch my login. It does that every once in a while. She gets on Zoom.
That's okay,
Right.
Nathan. I know it's you.
Okay, I'll be Anna today, or maybe I'll go by Nathan. We'll see. We'll see.
Well,
Hey,
she's
Nathan,
welcome.
you could change your name in here right now if you just right click it.
Oh, cool.
Oh, good for you guys. Okay. Computer gurus we got here. This is wonderful. Okay, we have Alex and Ryan and Nicholas and Brian.
Did you figure out? Yeah, okay, you got it.
Thank you.
Good going, you computer gurus. It's nice to be young. When I have trouble, I just look for a younger person. We have Julius and Bryce, Braxton and Regan, Nicholas. Got a good crowd. Okay, and let's see, what are we going to talk about today? Oh, it's 11 o'clock. It's time to get started. You guys did an exam, and I'm going to quit being lazy and grade them. How's that sound?
Mr. Griffin, I actually had a question real quick
Yeah,
about
go
the
ahead.
exam.
Yeah.
I was just wondering if you got my email about it, because I don't know, it might have been my connection that night or my computer, but I was having a lot of trouble trying to submit it through the Blackboard, and I emailed it to you.
That's fine. Now who am
Okay.
I talking to?
This is Daniel.
Daniel, that'll be okay.
Okay, I just
Don't
wanted to
worry.
make sure.
Don't worry. But I think the rest of them didn't have any problem. I don't know why that is. Anybody else have a question or comment before we're going to start the exciting chapter 3 here. First law of thermodynamics. That's what we're going to do. Unless you had a comment or question. All right, well, let's see what chapter 3 is all about. Chapter 3. First, it's the first law of thermodynamics. You will find it on page 60 in your book, and here it is. Let me write it down for you. First law, probably the most important law or equation. It's on page 60 in your book, and it goes like this. Now, they fancy it up by putting little numbers under here. That just represents the heat transfer going from state 1 to state 2, and that's the work done by your system going from state 1 to state 2. And what that is the total energy, the final, at state 2. And this is the initial total energy at state 1. Really what the first law of thermodynamics is, it's a energy conservation equation is what it is. See, there are 3 ways that you can change energy. Let me list them for you. To increase or decrease your energy, to change your energy. See, that really, that's just a change. if you write final minus initial, E stands for energy, or in this case, total energy. You can write it like that, delta E. There are three ways to change your energy. There's work. Your system can do work, or the environment can do work on your system. But there's work, there's heat. You can transfer energy by heat to a system and give it more energy, or you can transfer heat from a system to the environment, and that decreases its energy. And there's mass. There are three ways to change your energy of a system: work, heat, and mass. Now, see, mass itself has energy. And if you take some mass and shove it into your system, you've just increased the energy of your system. Or if you have a system and you take mass out and decrease the mass, well, that mass had energy. You know, you've heard of Einstein's E equals mc squared. That's energy. Mass has energy. And if you decrease the mass, well, then you decrease the energy. Yeah, there are three ways. Now, you need to know that in our book, work done by your system is positive. Work done by your system is positive. So like if you have a piston in a car and if it changes expands your piston, and that turns the connecting rod pushes your crankshaft, and that's connected by the linkages to your wheels through the differential and makes your car go, then that's that energy of your car engine is doing work. It's doing work on your car, and you can go up a hill. And that's positive work. Now, work done on a system, like if you take a car at the top of a hill and just let gravity, see, gravity is external. It's not part of your engine. It comes from the Earth's attraction, and it pulls the car down the hill. Well, that's considered negative work being done. If the environment's doing work on your system, that's negative work. See, the work done by the environment on your system is considered negative. Now, heat transfer, if you can take energy and you can transfer it into your system, they consider that positive. But heat can be transferred out. Take your system and stick it in a bucket of ice water. Well, that's going to cool it off, and energy will be transferred out, and energy transferred out is negative. And you know about mass coming in will be positive, mass going out will be negative. Now let's talk about, now we got the three ways to change your energy. Now they only have two ways here in the first law of thermodynamics. But see, this is the first law for control masses. For control mass, you don't have any mass coming in or out. So you can take this one here in this chapter 3. There is no mass coming in or out. We're dealing with control masses, so you don't have to worry about it. The only two ways to transfer energy are work and heat. That's heat, that's work. I don't know why they didn't use H for heat. Well, yeah, I do, because H stands for enthalpy, and we'll learn about that in this chapter too. So they can't use H for heat. They use it for something else called enthalpy. Any comments or questions so far? Well, we've given you the first law. We've told you a little bit about the pluses and the minuses. Now, let me just tell you one thing. You probably will never run into this, but there are a few thermodynamics books out there that have a plus sign right here. And they define work just the opposite. They say work done by the system is negative, work done by the environment is positive. But just don't let it worry you. We're going to go with our book. This is the way most thermo books do it. But if you ever see that, a plus sign there in a thermo book, they've just defined work differently. Everything's okay. It's just a little different. It's really, in some ways, more beautiful and consistent. It's too bad they don't do it that way, but this is the way we've learned to do it. We're going to do it this way. Any comments or questions on that? Okay. Now let's talk about each one of these. And then we'll work some problems. A little bit more theory, and then we'll work some problems. Now this E here stands for total energy. It consists of three parts: internal energy, potential energy, and kinetic energy. Now, internal energy really depends on your temperature. The hotter something is, the more internal energy you have. It depends on temperature. Potential, and there's tables of it. Only in what they have in the tables in the back, you can flip almost at random any place in the back here, and you'll find these values of little u. See, they use little letters. We can put all of these in little letters if you like. All they've done is divide everything through by your mass. Because you've got a control mass, it's fixed. There's no mass coming in or out. You have a certain amount of mass, and you can just divide. If you divide everything here by the amount of mass you have, they call that the total energy per mass. They call this your internal energy per mass. They have a name, they call it specific internal energy. This is specific potential energy, and this is kinetic energy per mass, or specific kinetic energy. And you know the equations for all this stuff. Well, you know the equations for these. This is mgh. I know you've seen that before. I hate to use that H because we use H for something else in this class, but I think that's what they'll teach you in high school. And this is 1/2 mv squared. Now, when you divide through by m, they call this a little e, a little u, and when you divide through by m, you just get zh. Only in this book, they can't use h, they use a z instead. Z just stands for how high something goes up, okay? And here, that's supposed to be a plus sign. And this will be 1/2 v squared. But now here we have it. We run into another problem. We use V, little v, for volume over mass. So we can't use little v for velocity. See, kinetic energy is 1/2 mv squared, where that's velocity. So what they do is they use this kind of a bold print V. Yeah, look in your book there. Any place in your chapter they have a bold print V. It stands for velocity. So I've talked to you about E now. I've talked to you about those. Let's talk about work for a little bit. Do we have any comments or questions? Okay, well, let's talk about work then. Before I do, let me go through these different values of V. This is kind of confusing. We have a little v, we have a big V, we have a bold face V, we have a V dot. There's even a little v with a bar over it. We have 5 different kinds of V's in this class. This is called specific volume. It's in cubic meters per kilogram. And if you go to the back of your book in the tables, you'll see little V's all over the place. That's what that is. I'm trying to find some. Yeah, there's some. And there's some more. They're all over the place. Now, this is volume, and that's just in cubic meters. This is velocity, and that's meters per second. This is volume. It's called volume flow rate. It's called volume flow rate. Can you guys see my, yeah, you can see that, volume flow rate. And what that is cubic meters per second. This here, you probably never see it again, but I'll just tell you, it's called molar specific volume. And what that is cubic meters per kilomole. I don't think you will even be using that. Kilomole, there you go. So really, basically, there's just four different V's for us to keep track of. Now we're going to talk about work, unless you have a comment or question. And then we're going to do some problems. I need the room here, so say goodbye to all that wonderful stuff there. First law. Keep in mind now, this is for control masses. When we talk about control volumes, that's going to be chapter, I think it's chapter 4. See, we're in chapter 3 right now. Hope you can read my writing. All right, great. Well, let's talk about work. This is in the book. It's on page 62. And you all learned what work is. They use W for work. And it's force times distance. It's just force times distance. You've learned that. It's like Newton meters. Or you could call it joules. Same thing. A Newton meter is a joule. Now, if the force varies, then you have to use calculus. And you have to go F, D, X, ds, some kind of a dummy variable there. They use an S just for distance. So you have to use calculus if something's changing on you. If the force is constant, you don't need to have the integral there. Now you all know that force is equal to pressure times area. So we could substitute pressure times area ds. In the case of a piston, you could have a dy. Here's this piston. Let me draw it for you. Here's a piston. And we're gonna maybe have some heat transfer in. It'll make it hotter. The piston will go up. And at state 2, it will be hotter. It'll be hotter. The piston will go up. And this little distance that it goes up is your dy. See, it goes up a distance, dy. And the piston itself has an area. Here's this piston. It has an area. If you multiply by how much it goes up, you could say that that's equal to P dV. So the work done is P dV. That's the work. Now, if you wanted the work per mass, see, that's your work divided by your mass. That's the integral of P d little v. Because, see, big V is V over M. Well, that's little v. Get it? This is why your PV diagrams are so important. The area under your PV diagram gives you the work per mass. Let me draw you that. If you have a PV diagram, big V, P, and you go from 1 to 2. There you go. State 1, state 2. The area underneath that graph is the work done. But see, if you have a PV diagram, it looks similar. It's just that the area under the P little v is the little w. It's the work per mass. And we're really more interested in it. That's why PV diagrams are so important. And notice the work done depends on the path. So you could get from 1 to 2 by doing this, like that. But that has more work because the area under that, can you see that the area under that is bigger than the area before? So work depends on the path. See, a lot of things don't depend on the path. Like, for instance, the change in temperature. At state 1, you have a certain temperature. At state 2, you have a certain temperature. It doesn't matter which path you take. The change in temperature is the same between any path between 1 and 2. But the work differs. The work is different. It depends on the path. See, for any kind of property, temperature is a property, pressure is a property, specific volume is a property, specific internal energy is a property. Any of these things, the change in any property does not depend on the path. In fact, that's part of the definition of what a property is. The path doesn't matter. The change in your property is independent of the path. But it turns out work depends on the path. You can see that if you went down this way from 1 to 2, the area under that graph is a heck of a lot smaller. So the work depends on the path. Work is not a property. Work does not exist at state 1. Work does not exist at state 2. Work is something that you have to go from 1 to 2. It takes time. It takes time to do work. Temperature, it doesn't take time. You have a certain temperature at a given instant of time. And then later, at some other time, you have a temperature. You don't care how long it took you to get from that first state to the second state, because temperature is a property. It does not depend on your path. Well, that concludes the wonderful theory for right now. And now we're going to work some problems. Do you have any questions? Okay, well, we're going to work some problems. What about homework? Do you have any homework? I don't know. Let's look and see here. I bet you do. Homework. Let's see if we have any. Today's the 15th. Yeah.
I have a question.
Yeah, we have two homework problems, 360 and 368. They would be due, what, Friday? What's today, Tuesday? I think Friday. Go ahead, I'm listening to you.
Can we please work problem number 3.68?
Okay, now just a tiny minute. 368, I think, is on your homework. And I want to see what you can do. Ask me next time and I'll do it. Who am I talking to?
Talking to Reagan.
Reagan?
Yes.
Reagan, I want you to try it. Now let me go through the problems, Reagan. This might help you. They have this in the book. It's on page okay, just a minute now. Totally organized as always. Yeah, here we go. It's on page 80 in your book. They have 5 steps there. But I have a slightly different, Reagan, steps to solve thermal problems. Here we go. Now I do this every time. And in the book on page 80, they have a 5-step process. Let me give you mine. Number 1, draw the device sketch, Reagan. And we've done this many times before. You know, a piston or whatever. Draw the device sketch and label it. Label it with the properties, the pressure, the temperature. Label it if there's any energy transfers like heat or work. And if you have a state 1 and a state 2, draw 2 diagrams, 2 sketches. Label them. Number 2, you've got to decide on some things. Is that how you spell decide? I think it is. Right? You've got to decide, well, are we dealing with metric or English? It would be nice to know. You've got to decide, are we dealing with tables? Are we dealing with ideal gas? Are we dealing with compressibility? You've got to decide that. You've got to decide, do we have a control mass or a control volume? You have to decide some things. And then what? Well, then you draw a PV diagram. And haven't we done many of those? And label it. Label it with the pressures and temperatures. And don't take any shortcuts. Remember, I've told you no shortcuts. If it's an isotherm, follow the isotherm. And then you do your math. If it's, we have different equations. We have one that goes like this. If you're using the tables, for instance, you do some math. You put in the numbers yourself. Or if you got an ideal gas, PV equals RT maybe, you do the math. Let's see what they said. Make a sketch. Well, that's the system, yeah. Define, yeah. Control volume, control, yeah. I just told you about that. Transfer into and out of, that's heat transfer or work, yeah. Number 3, the laws. Yeah, that's what I'm telling you. The first, hey, well, I'm forgetting something here. You need your first law for sure. And later, we'll learn the second law. And other equations, like that one or that one. Then you do your math. And what do they say on page 80? Write down different laws and equations. And combine, do the math. They finally get around to doing a PV diagram or a TV. I haven't really talked about TV. PV is adequate. All you gotta do is a PV to make me happy. I put that right here. They don't put the PV diagram till down here someplace. And then step number 6, check your work. Check it and see if it makes sense. We'll try to go through. I've done this with you, and we'll try to do one here today together. So Reagan, do that. And you know what? Most students have trouble with this right here. If they have trouble with a problem, that's usually where it is, right there. Okay, well, let's work some problems now. Anybody else? I'm going to erase all this and do a problem. I'm going to do problem 336 with you guys. Did you have anything to say before I erase all this? All right, well, let's do that problem. And what I'm going to do this. See these steps right here? I'm going to try to do those steps. I do it every time. And if you have trouble doing thermal problems, it's probably because you're not doing these steps. You're probably forgetting something. Okay, now this is 336. Let me find it. .336. It's an isobar. Piston cylinder, 2 kilograms of water. So I can tell you right now, I'm going to use the tables. Let me write down some stuff. We have 2 kilograms of water. I want to use the tables. It's at 20 degrees Celsius. It has a volume of 0.1 cubic meters. Somebody locks the piston, preventing it from moving while we heat the water to saturated vapor. Find the final temperature, volume, and the work. Okay, that'll be fun. Let's draw the device sketch. Isn't that one of the first things to do? Here's state 1. Here's a piston cylinder. That's what they said. state one. What do we know about it? Well, it's 20 degrees Celsius. We have H2O in here. We have 2 kilograms. I can tell you what the specific volume is because they give you the volume and they give you the mass. And I'm getting 0.05. How about you? Make sure I did that right in my head. 0.1 divided by 2, I think is 0.05. So we have the specific volume. We don't have the pressure. We know the temperature, but let's get the pressure. Pressure is, how would we get the pressure? Let me ask somebody. Let me go to my friend here. Nicholas, unmute and say hi, Nicholas.
Hi.
Hi. Nicholas, my question is, can we use PV equals RT? Nicholas, can we go PV equals RT on this?
Yeah.
Sorry, Nicholas. The answer is no.
No?
No. It's water. Water is not an ideal gas. Let's draw the PV diagram so we'll find out, Nicholas. We're going to do the PV diagram. Isn't that like number 3 on my list that I just gave you guys somewhere in there? It's up front, I know that. We want 20 degrees Celsius. Help me find 20 degrees Celsius. And you know what? It's way at the top of your vapor dome or your table. I'm on table B.1.1, and we're going to draw this 20 degrees Celsius isotherm. And if you're at the top of the table, you're down here at the bottom of the vapor dome. It just kind of works backwards. There's your 20 degrees Celsius. There's your 20 degrees Celsius. And you can get this pressure right here. They call it the saturated pressure. Now, I don't know that that's P1 or not. I'm still thinking about that. But that saturated pressure at 20 degrees Celsius is 2.339 kilopascals. Now this right here, this is VF, and that is 0.001. So you can get a lot of stuff off of these tables. This is VG, and that is 57.7887. And now we're going to find out where we are. You know what I think? I think we're in here someplace. I think state 1, 0.05 is bigger than 0.001. I'm sorry, I'm right in the middle of a class right now. Can you try me later, please? Okay, I need to teach my class. Okay, now let's see, where were we? Oh yeah, look here. The specific volume here is 0.05, which is bigger than 0.001, but it's smaller than 57. So we're in here. Okay, good. Now what? Let's read it. 336. Piston cylinder contains 2 kilograms, blah, blah, blah. State 2, you know what? State 2 has got the same volume. Nothing changed because somebody locked this piston. It's got the same volume. State 2. Well, what's different? What's different is they put it on the stove. They put it on the stove and it got hotter. I think the temperature is going to be hotter, but what will it be? I don't know. Let's see what it says. Someone locks a piston. Oh, they come up here to where it's saturated vapor. That's what they did. Here's state 2. And what do we know about state 2? Well, it's the specific volume is the same as it was at 1. It's 0.05. We need to find a specific volume that has, it's a saturated vapor that has a specific volume of 0.05. So go to your table and help me find water. Okay. I'm looking for water here. Yeah, okay, there we go. Now what I need is, I'm looking for a VG of 0.05 for water. Okay. Well, I don't see any there. Hey, here's one. Yeah. You know what? Let me write this down someplace. Need some room here. I need some room. We need 0.05. They don't have a 0.05, but they have a 0.05013. And they have a 0.04598. And what are we supposed to find? Just a minute, I got lost. 336 says here, find the final temperature, volume, and process work. Okay. Well, the temperature for the 0.05013 is 0.045. I got lost there. I need 0.05013. Yeah, there. That temperature is 250 degrees Celsius. The temperature here at 04598, 04598. There it is, 045. That's 255. Now, can you guys find these numbers in table B.1.1? Look at table B.1.1 and see what we want is we want 0.05000. Can you find those temperatures? You guys know how to do that? How about Nathan? Nathan, can you do that?
I can find it. The question is, can I interpolate?
Oh, I know you can. I'm gonna interpolate this. Gee, it's awfully close to that one, isn't it? I think our answer is going to be probably around 251 or something like that. You see how close these are together? Yeah. Okay, I'm gonna I want you to do that, and I'm going to do it, and we're going to find the temperature now. Here goes. I'm interpolating, and you need to interpolate. Go for it. Okay. All right. Yeah, guys, I'm getting I'm getting 250.16. I told you it was awfully close to that. It's dang close to 250. So I think we have the temperature. What else did they want? Find the final temperature, the volume. Well, the volume's the same. And why would they ask us that? Just to confuse us, I guess? I don't know. Oh, we never did get the volume, did we? Well, see, the volume is going to equal the mass times the specific volume. We know the specific volume. It's 0.05. And we know the mass. It's, I'm kind of confused here. They gave you the volume. The volume is 0.1 cubic meters. That's given in the problem, so that's kind of ridiculous. Find the final volume. Well, it's the same as the initial volume. The work. There is no work. The work is 0 because you have to move the piston in order to do any work. So we're done with that problem. And I tried to follow the, did we ever get the final pressure? They didn't ask for the final pressure. Did they? We got the final temperature. We never did the final pressure. Well, just a minute. I bet we could. To get the final pressure, we would just need to, got lost there. Yeah, there we go. You would have to put in these pressures. See, this pressure here is 3973. And this pressure here is 4319.5. So to get the final pressure, you know what? It's so close. It's going to be real close to this. I don't want to do it, but you could interpolate and get the final pressure. They didn't ask for it anyway. So we're done with that one. Any questions on that one?
I know I'm back, but this is Nathan.
Yeah.
But I think I did my interpolation wrong. I subtracted. I did 0.05 minus 0.04598.
Yeah.
Is that wrong?
No, that's not wrong, Nathan. It's just that you're going to have to subtract to get the answer.
Subtract.
Yeah, because see, it's going to be smaller than 255, right? You're kind of doing it backwards, but it's okay.
Yeah, because I got like a different number. But all right.
Well, what you did was you subtracted these two, right, Nathan?
Yes, I set
Yeah.
my fraction correct, and I don't think I am.
Right. Here, let me do it. Nathan wants to do it that way. It's okay. if you did it the way Nathan did it, then you have 0.05000 minus 0.04598. And then you divide by the total difference, which is 0.05013 minus 0.04598. And you get, let me do it again. I must have done something wrong. 0.05000 minus 0.04598 divided by 0.05013 minus 0.04598. Yeah, and what you get here, going from here to here is roughly 97% of the way, Nathan. It's really 0.9687 to get from here to here. So what you do is you take this difference, which is 5 degrees, and you multiply 97% of 5 degrees, or 0.9687 times 5, and what you get is 4.843 degrees, and you have to subtract it. If you take 255 and you subtract 4.843 degrees, you should get the same answer I got. Let me see what you get. Plus 255. You get 250.16 degrees. Well, that's what I got. I got 250.16. So you can do it that way. Did that make a lick of sense, Nathan?
That did. I just need to practice it more. Thank you. That worked.
Yeah, sure. Well, we got time for another problem. We don't quit till what, 12:20? Yeah, let's do another problem. I mean, aren't these fun? Yeah, we're going to do another one. Now, the one I want to do now is 363. It's an isobar. I'm going to erase all this now. But you see the method. You do a device sketch. You label it. You do a PV diagram. You label it. You write some equations. What equations did I write? Well, I wrote some. I wrote little v is volume over mass. That's an equation. And then I had to interpolate the table. Okay, yeah. And then you get your answer. And I'm going to do another one now. This one here is an isobar. Oh, on that 5-step method, I forgot to mention, look for processes. See, there's various kinds. There's isocores. That first problem we just did was an isocore. And now we're going to do an isobar. And there's also isotherms, etc. And we're going to learn a lot more, but there's different processes. You have to be aware of your process. Now, the one we're doing now is 363. Here we go. And we're just illustrating the method by which we do thermal problems. I do the same thing every time. And if I keep hammering this into your heads, you'll get it. Now this says a cylinder fitted with a frictionless piston has 2 kilograms of superheated refrigerant R134A. Let me write that down. We're going to do R134A. So we're going to go to the tables. We are not going to use ideal gas. The rule is, if you have a table, you use the table. We don't use the ideal gas formula when you have a table. Now the pressure is 350. kilopascal. Temperature is 100 Celsius. Cylinder is now cooled to constant pressure, reaches the quality of so-and-so. They want the heat transfer. Okay. Well, we're going to decide what we're going to do. We know the process is an isobar. They told us that. We know it's a controlled mass. We know we're doing SI. We're not doing English. When you have Celsius and kilopascals, that's the metric stuff. We know that. And what else do we know? Let me read this again. It's 363. It says superheated. Hey, we already know we're in the superheated region. Let's draw that. Here we go. I think step number 3 was to draw the PV diagram. And you know what they kind of look like. They kind of look like that. And let's go and find the R134A in the back. Start snooping around. Help me find R134A. Okay, of course, I'm flipping through pages here, and you guys are working your computers there to find it. Yeah, I found the R134A. Now I need 100 Celsius. Gee whiz, 100 Celsius is almost at the bottom of the table. So you know what that means? That means it's almost at the top. It's right here. Here's your 100 degrees Celsius. We know, though, we're out here someplace because they said so. This region is called superheated vapor. We know we're in superheated vapor. Okay, now this pressure here, according to the table, at 100 is 3973. This is 3973 kilopascal, right there. But we don't have that. We have 350 kilopascals. Well, you know what? 350 is a whole lot smaller than 3,900. It's down here someplace. 350 kilopascals. That's a lot smaller than 3,973. So help me here. We're going to come over here. Bingo. There's our state 1. Now it's in superheated vapor. So let's go to the superheated vapor chart and find out some information. What do we know? We know it's 350 kilopascals. Do they have a 350 kilopascals out there? Uh-oh. Auga. They don't have it. You know what they have? They have 300 and 400. Well, we're lucky that's right exactly halfway between, right? So we could get the specific volume. And while we're at it, we'll get the specific internal energy. But to get it, won't we have to take halfway between 100, let's see, between 0.09861 and 0.07325. And if you take halfway between them, you'll get your specific volume at state 1. Let's go ahead and get the specific internal energy at state 1. It's going to be 460.9 plus 460.9 plus 460.22. But see, it's halfway between. They don't have a 350, you understand? We got to go halfway between 300 and 400. Did I lose anybody? If I lost you, speak up. Now let's go ahead and get these numbers. Here we go. 0.09861 plus 0.07325. Hey, I found the specific volume. I don't know if I got enough room to write it there. Let me write it down here. Specific volume is 0.08593. And the specific internal energy is, I haven't done that yet, 460.9 plus 460.22 divided by 2. I got a bad feeling that I might have lost somebody along the way here. Let me call on somebody and ask them if they're following this stuff. Reagan, let me ask you, Reagan, are you following what I'm doing here, Reagan?
Yeah, I got a little bit lost. I'm trying to figure it out.
Can you find these numbers that I'm coming up with, Reagan? Can you find that 3973 and these numbers here?
Yes, I can find the V1.
Good.
On the U1, I'm having a little bit trouble on the U1. Can you
Okay.
please? Yeah, just
See
right
if you
there.
can find the 460.9, Reagan.
Okay, let me try it.
It's where it's 100 degrees. If I did that right, let me double check that. I could be wrong. I
Because I can't
lost my
find it.
place. Well, let me find it here. Reagan, you need to be on table. I got lost here, Reagan. Let's see. We need, yeah, here we go. You need to be on table B.5.2. Can you find B.5.2, Reagan?
Yes, I can.
Now, they don't have a 350. See, we need 350.
Mm-hmm.
But they have 300 and 400. So what we're going to do is we're going to write the U at 300. That's 460.9.
Mm-hmm.
And the U at 400, which is 460.22. Can you find those?
Yes, I can.
Divide by 2 to split it in half.
Yeah.
I think you're back on track.
Yes, I did now.
Good.
Thank you.
I think Reagan's okay. Now, let's finish this problem here. What are we supposed to do? I got lost. Let's see, the cylinders. Oh, we're going to cool it at constant pressure until it has a quality of 25%. Well, here's our process, guys. We're going to follow this isobar. See, this is an isobar. And we're going to cool it all the way down to here someplace to state 2. At state 2, the quality is 0.25. Did that make sense? We're going to cool it. I never drew my, doggone it, I never drew my device sketch. Here, let me do that. Here's your state 1. There's state one. And we're going to put that in a bucket of ice water, okay? And you're going to have a heat transfer out. Now, I don't know what this temperature is right here. But I can easily find out. It's, I keep losing my place. I need the R135A and I keep losing my place. It's around 350 kilopascals. And that's dang close to 5 degrees Celsius. There's a 5 degrees Celsius line running through there almost. We're going to really cool it off. We were at 100 degrees Celsius, but when you get to here, it's 5 degrees Celsius. Man, we've cooled off 95 degrees. That's what happens when you put it in a bucket of ice water.
I'm sorry, where did you get the 5 degrees? Was that just on the table? I missed that, sorry.
Yeah, and now who am I talking to?
Nathan.
Yeah, Nathan. Nathan, look on table B.5.1, Nathan. It's table B.5.1. Thank you for asking, because I didn't really explain that. And what you want is, you want, I got lost now. How did I do that? Oh, it's an isobar. Remember, we're going to follow the 350 kilopascal isobar. It's an isobar, so the pressure is 350 kilopascals. Now, if you look on that table, at 350.9 kilopascals, it's 5 degrees Celsius. Can you see it, Nathan?
I do see that. So that's just close enough to call it good, or?
Well, if you wanted to interpolate it, the truth is it's probably about 4.99 or something, okay?
Okay.
But it's awfully close to 5. It's dang cold, we know that. It was 100 degrees and now it's only 5 degrees. So that makes sense. Now what are we supposed to do with it? Let's see. And cool, constant pressure, calculate the heat transfer. Okay. Well, we have an equation called the first law of thermodynamics, and I'm going to make some room here. And it goes like this. We're going to use the little letters. Now, the change in U, you know what that means? That means little u2 minus little u1. Well, we got little u1. Here, let me circle that. We got that. And we can get little u2. Here's how to get little u2. It would be the UF plus your quality times UFG. We can look those up, can't we? We can look those up. Again, I'm going to cheat, Nathan. And instead of interpolating, I'm just going to go with 350. And the UF at 350 on that table, B.5.1, is that what it is? Is 206.48. 206.48 plus 0.25 times 174.38. Now, if you want to interpolate that, you can get a very slightly different answer. But see, we can get our U2. Look here, we can get our U2. You can see it. All you got to do is plug your calculator there. Now, this Q is what they want. Let's put a little mystery cloud around that. Actually, what they want, if you read it, they want big Q. But see, big Q is just m times little q. If we could only find the mass, we could get we could get the little q. But how would you find the mass? Oh, they give you the mass. Did you see that? They give you the mass as 2 kilograms. To find the mass, you could take the mass is equal to I got lost here. Just a minute. They give you the mass. Yeah. It's given. It's just, I don't know, 2 kilograms. Yeah. It's given. And if you can ever get this here, you can multiply and get the big, this is what they wanted, really. But if we can get this little q, we can do it. Now the work. Do you remember I was telling you that the work is the area under the graph? Didn't I tell you that earlier today? Here's the area under the graph. It's a rectangle. Here, let me color it. We're going to color this. See, here's state 1, here's state 2, here's our process. It's an isobar from state 1 to state 2. I never drew the state 2. Well, let's draw it. Here goes. Now the volume goes smaller because we got colder. We got much colder. We were 100 degrees Celsius. And now we're what, 5 degrees Celsius? Is that what we, yeah, 5. We're 5 degrees Celsius. Plus we have some liquid down in here. This is not all vapor. See, this is all vapor. What about the pressure? Well, the pressure doesn't change any. Don't put any weight on here. It's the same pressure that it was before. It's an isobar, but there's your device sketch. Now, how do you get this area here? Well, they taught me in school the area of a rectangle. It's the base times the height. Well, what's the base? Well, the base would be V2 minus V1, and the height would be 350 kilopascal. So that's the height, 350. The base is V2 minus V1. Well, do we know V1? Yeah, we know V1. What about V2? Do we know V2? Well, we could get it. We can certainly get it. Look here. Let me write it for you. V2 is going to equal the VF at the 350, which is 0.05755, no, 0.000783. Plus 0.25 times 0.05755. 0.05755. Okay, so we have calculators. We can get V2. We can get V. We know V1. We can get the area under your graph. which is equal to the little w from 1 to 2. Okay, from 1 to 2. We can get it. And from there, you can get little q. And once you get little q, I erased it, but big Q is just equal to the mass times little q. That's how you do your problems, and we can go ahead and get those. I have the answers. Well, let me see if I have the answer. Just a minute. This was 363, right? Let me dig around here. 363. Yeah. Okay. We got time to do this. We have 5 minutes, and you can very definitely get V2 and V1, and you can get little w. Go ahead and get those. Go ahead and get V2, V1, and little w for me. Can you do that? I'm going to do it, and we'll see what I get. Well, I think I got V2. I think V2 is 0.01517. And I'm going to get V1. I think I got V2, or I mean V1 is 0.08593. And now I'm going to get the little w. Okay, I think I got little w, guys. I think the work per mass, it's a negative. See, it got smaller. The environment's doing work on it. I got 24.77 kilojoules per kilogram. So I think I got that. Did we ever get U2? Yeah. Well, no, we didn't. I need you to, I'm going to go ahead and solve this and get the heat transfer. Here goes. You have to get that U2. I'm getting U2 is 250. So I need a little room here. We'll write this out and we'll finish this thing off. I just need a little room here. U2 is 250. These are kilojoules per kilogram. U1 is 460. I don't know, 0.6 maybe. We're going to get little q here. And the work, now watch it, there's a minus in the first law, but the work itself is minus 24, rounded off to 8. And so you can solve for, you can solve for the heat transfer per mass will be well, I'm getting negative 235.3 kilojoules per kilogram. And if you want the actual heat transfer, not the heat transfer per mass, you have to multiply by 2 kilograms, right? Isn't that what they said? Yeah. So you take the 2 kilograms times that, and you get a minus, we'll call it 471. I'll just round it off. Now let's see what my answer book says. I've got an answer book here, and they said, if you're careful with all the numbers, make a little room down here. The book says that the heat transfer is negative 469.2 kilojoules. I kind of got lazy and rounded off, and I got a negative 471 kilojoules. I think we did okay. That's how you do it. It's sad, but our time is up. But we've shown you how you do these problems. It's a step-by-step method. It's sad we have to go. And let's see now. What about your test? You did your test, right? I just need to grade them. That's what I need to do. I think there's some homework. Look on Blackboard. I'm going to have to go. Any last comments? Going once.
See you Thursday.
Hey, see you Thursday. It's a deal. See you Thursday. Ta-ta for now.